Hi, Kyle.
So hopefully you had the opportunity to read through this first page as I asked. So what this describes is the ray model of light. We've talked about the wave model of light, which is shown in the figure on the top right. The rays, though, are radial lines drawn in the direction of a wave's motion. So let me switch the document camera here. And all of the videos that I'm going to show you today are in the movies on reflection right below this figure. So we have these figures showing rays of light coming from a source. They're in the direction of the wave motion. And the reason we do that is to show how light is blocked out or reflects or refracts for this section. So this first picture here is showing as if I had a flashlight and I was pointing it towards the screen. You could even think of this light source here as being the projector projecting light towards the screen. So what we have is a card with a small hole in it. So everything's blocked out except for the single hole. And we're wondering, what is the light going to be like when we shine light through that hole? So let's go ahead and watch our video, and I'm going to show you guys what happens in that case. So here we have a small hole in this piece of cardboard, and then we have the light on the piece of paper. Now, what does it happen to the light on the screen as the person moves their hand to the right?
Like that little dot?
The little dot moves
To the opposite direction.
to the left, and as they move up, it moves down. Right. So you guys are going to need a ruler to complete this activity. If you don't have one, go ahead and grab one out from here. And we're going to draw a ray model to describe this. So let's go back to our document camera. And we're going to draw a ray of light through that hole so that it lines up with where it goes on the screen. So there's rays of light coming out in all directions here, right? But only this light that goes through the hole is going to create a light on the screen on the side view. The front view of the screen, however, will have light in the middle on the bottom, right? So that's what our side view is going to look. Our side view moving through the line and then moving through the hole to the screen, and then our front view of what the screen looks like.
Is that just a filled in circle?
Yeah.
Okay.
So it's basically, this is the light being projected through the hole, and then we're rotating this and looking at it at the front, the light projected through the hole and hitting that screen. So this is the view that was on the video. And this is our side view. Now, is this the only ray of light that's leaving the light?
No.
No, there's light rays leaving in all other directions. What happens to these other ones? They get blocked by the screen. So we can draw those as well. And yep, so we can draw those other lines showing what happens. So now let's go ahead and do a little predictive game. Go ahead and hop on your phone and go to Socrative.com. You could go on your laptop, yeah, if you have your laptop open. Yep, and type in, go in student login and type in Johnson 9761.
Erase. Go to student login.
Yep. Johnson 9761. I'm going to open up a multiple choice here. See, 2 students have gotten on. Let's go back to that question. Imagine that you held 2 magnolites, one above the other, as suggested in the picture below. What do you predict you observe on the screen? Now, we're in chapter 18, the ray model of light. This hole is much bigger than our wavelength of light. So don't think about chapter 17 stuff with diffraction. We're thinking about chapter 18, rays of light, not interference of waves. What will happen when we have 2 magnolites? Go ahead and answer. A single spot, B, 2 spots, C, a continuous line, or D, there'll be no illumination.
2 magnets and 2 light sources?
Yep. So instead of 1 light source up here, we now have 2. What's going to happen on the screen behind the blocked out pinhole? All right. So it looks like we have more students for B, 2 spots of illumination, and 1 for A, or a few for A, about 50-50, a single spot or a double spot. So let's go ahead and check and see what happens. So here we have 2 light sources in a single pinhole. All right, so what do we see? 2 spots. And here, the arrangement are these are side by side. And where are they on the screen? Side by side. All right, so go ahead and flip to your next page. What will happen if we block off the upper light source? No, sorry, that does not happen here.
It's on the
It's at the very bottom.
It's on the very bottom.
Okay, yeah. If you were to cover your finger over the top hole of the top light, which spot do you think would disappear?
Bottom.
The bottom one. Now go ahead and draw a ray diagram and try to explain that with your ray diagram.
Is that on the second?
Yep, on the next page. So I'm going to draw a ray going through the hole, giving 1 spot, and then a ray through the other hole, going to the other spot. So we have 2 spots now, and we can see that if I block out one of them, the top one, the bottom light is going to disappear here. Again, we still have rays moving in all different directions, right? So we can draw more rays coming from this source, but those other rays are going to be blocked out. So draw a few more rays reaching the screen, getting blocked out, and the only ray that comes through is the ray that goes through the hole. So when we draw ray diagrams, we could draw infinitely many rays in all different directions. However, we typically only draw rays that are important to us. Important ray is the ray that makes it through the hole, as well as a couple of rays that hit the screen, saying that all light is blocked out except the light that hits the hole, because it goes through it and then hits the screen. So go ahead and continue reading through that. This will talk about those rays, so take a second to read through this next page. So our boundary rays are important. So now see if you can use your ray diagram to describe over what area of the screen will be blocked out if we now have a blocker. So instead of a pinhole here, we now have a blocker. It's blocking out a shadowed area. The rest of it's illuminated. This is if it's in line with the blocker. What's going to happen when we move the light upward? Where's the shadow of the blocker going to be? On the bottom of the screen. And how do we draw that out using our ray diagram?
Light going through the edge.
Yep, so you're going to want to include boundary rays. Light hitting the edge of the blocker. Oops.
And still going through? Or,
If it hits just the edge of the blocker,
oh,
it's going to go to the screen. But if it hits the blocker, it's not going to go through. So here, this area is the shadow, and this area has light. I think we have a video for this as well. So let's go ahead and see this. So we have a blocker. When we move to the right, the shadow moves to the left. When we move to the left, the shadow moves to the right. We move down, the shadow moves upward. And when we move up, the shadow moves downward. So then this is what's going to be appearing on the screen, right? This is what's going to be shadowed out. And then the next one says we move the light a little bit closer to the blocker, a little bit closer than it is right here. What's going to happen to the size of this blocked out shadowed area? So go ahead and draw your ray diagram and say, gets smaller, gets bigger, moves, directions. So those are the boundaries. So everything behind the blocker is shadowed. Pretty much the entire screen is blocked out.
okay.
Here, when it was further back,
Or
we
is
only
that
have
the top one? Oh, wait. Oh, the whole screen is back.
yeah. So as you
This
move
literally be this whole thing.
yep, as you move the light closer to the blocker, all of the light gets blocked out. Yep. We could also consider this a larger angle. Here, there's a small angle of light that's getting blocked out, whereas here where it's closer, there's a larger angle of light being blocked out.
Okay, that is great.
So all of the screen is getting blocked out here.
I have a question.
Mm-hmm.
How did you know where to place the block on the first one? Like, how did you know that would be the width of it on the screen?
I just assumed that it was the same width as this blocker. It was a square blocker, so I made it a square. Okay. So this has to do with reflection, right? This is leading us into reflection because when light reflects, instead of going in a straight ray, it reflects off of an object and comes back out from the mirror surface. So think about this. Say we had a flat mirror and part of the mirror was blocked off so that we only had a strip of mirror visible. If we had light coming to the mirror at this angle, so we could draw a ray coming out from the light source and hitting this small strip of mirror that's visible, where among these positions, A through E, will receive the most, will be able to see the light? So go ahead and go on to Socrative and answer that. If light is coming from the light source here and hitting this narrow strip, will it reflect back to D or E or C, or reflect over here to A or B or C? How will it reflect? Looks like 5 out of 8 have responded.
Zeb and I are on the same one, so.
Okay.
I'm just writing letters with no answers.
Broke the website.
What
Way to go.
It just says like A through E, but like nothing else. Like that's all I get.
Oh, that's how mine
Is that
is
how
too.
yours-
Yeah, that sounds all.
That's how mine is. I just pushed two.
All right. So most people are saying B. 86% here are saying B. And I agree with that because as you learned in the lab, the tutorial that you did, the reflected light comes out at an angle that's the same as the incidence angle. So looking at this, that means that we draw a normal line here, and whatever angle this is, this incidence angle, is going to be equal to this other angle here, this reflected angle. So I make it approximately the same, and it goes to that position. And this is the law of reflection. The law of reflection has a few things defined on it. We have our incidence ray and our reflected ray, and both of those rays are measured with respect to normal. Now for us, this is not normal, right? Because normally our angles are measured from horizontal. So you need to remember that rays are always measured from normal. What does normal mean? Remember from normal force? Mathematically, what does normal mean? You say perpendicular? Yep. So wherever our mirror surface is, here, this horizontal mirror, we have a normal line perpendicular to that. If our mirror was vertical, then our normal line would be horizontal. If our mirror was at like an angle like this, our normal would be at this angle. So normal is always perpendicular to the surface. Our angle of incidence is reflected or measured from normal, and our reflected ray is measured from normal. And those two are equal. Before you go ahead and practice that bottom problem, I want to take you to chapter 18 tutorial. Now, I will point out that I changed the grading for these tutorials. So you have unlimited attempts for your tutorials in chapter 18, both part 1 and part 2, because there's these ray diagrams. And mastering physics is pretty particular. Some people were able to satisfy the mastering physics gods, and others were still struggling with it. So I also made it no deductions for any questions besides multiple choice. So multiple choice question, you'll still get minus 10% each time you get it wrong. Whereas unlimited attempts for these other types of problems, numerical problems or ray diagram problems.
And that's for the MP too?
No,
Okay.
no, this is just for
Okay.
tutorials.
Gotcha.
Yeah, there's no ray diagrams on the MP set. So for this problem, this guy, Vittorio, wants to clean part of his mirror so that he could see his logo on his shirt. So for this one, you want to increase this incidence light coming from his shirt. And I'm going to start out with maybe a length of 4. And then I'm going to decrease his angle, because this angle is measured from horizontal, like I said, normally it is. And then increase its length. And then that light is going to come to his eyes from that light coming out. So let me see if this takes it. Okay, it took it on the first try there, but maybe because I practiced this a few times. But normally it's not as nice. This angle is 173.7, and this angle is 6.2, meaning 6.2 above and 170, or the 173.7, meaning 6.2, 6.3 below. So those two angles have to be relatively equal. If you're having trouble with this, getting those to look identical, reflected across the normal line, we can talk about it later this week. Or maybe I'll just make this one extra credit if it worse comes to worse. Same thing for this one. You want to make this line from his shoes to his eyes reflect perpendicularly.
Mastering physics was really picky in particular. We were adding, subtracting vectors.
Yeah, it's pretty particular about vectors, and that's why I gave the unlimited attempts on these. So go ahead and practice this idea. In the system below, all values, find all the different theta values, theta 1 through theta 6. Now theta 2 is going to be the easiest, right? What is theta 2 equal to? Yep, it's going to be the same thing as theta 1. And then how are we going to figure out theta 3?
90 minus 8.
Yep, because it's a right angle between the normal line and this horizontal surface. And then we use this triangle to find theta 4, and then continue to find theta 5 and theta 6. So go ahead and take a minute to do that real quick.
I was wondering, is that small? That's what I calculated.
Everyone doing all right with that?
Why do you take this to triangle? Or am I looking at that?
No, we're making this the triangle here. We're finding theta.
Oh, okay.
So we're getting alpha, we have theta 3.
Oh, we're giving alpha? Oh, okay.
So-
That's easier.
Or Mm,
Versus
I don't know.
too small. You know what I mean?
Yeah,
Everything.
yeah.
So how else do you
Because this is the triangle here.
I was going with the.
I think you just try to tell people to say range.
Yeah.
Oh my god.
Yeah, this has the same quality.
This would be
I
85.
find them in my hair.
65 plus
Like
30.
just I'll just do this and long hair just comes like in between my fingers. Ugh.
All right. So I think everybody got there. You solved for theta 4 before you solved for theta 5, right? Using that triangle. This is something I think that's on your tutorial, but you just in terms of theta. So you have to write with thetas, not numbers.
So it keeps making you solve it in terms of theta.
Yeah.
Yeah.
Mhm.
That was kind of
But it's interesting because, yeah, this theta 2 is equal to theta 1. So theta 3 is equal to 90 minus theta 1. And then theta 4 is equal to, in terms of theta 1, you
Right.
could always relate it back to theta 1.
right.
You're like, they're trying to show it as. All right, then go ahead and flip to the next page and read through this.
Can you add info? So 5 of these, and then this one would just be. Because this is what you want to use. With those. Thank you. Okay. Yeah, you're right with that.
Okay, hopefully you've had a chance to check out that next page to read about virtual images, this virtual image that's produced behind the mirror. I'll go ahead and open up this simulation so we can take a look at it. So I just copied down this O-Physics simulation, plane mirror reflection simulation right here. That's where I got these images from. So we have an object and a mirror. And what's this dashed yellow line? That's the normal line. So how does this angle here compare with this angle? The same. Now we also, if I was sitting here looking at this mirror, there's an object up here and I was looking at that image, it would appear to me as if the image was somewhere over here behind the mirror, right? So this is called a virtual ray. It appears as if this image is emitting a ray into my eye from that mirror surface. So that's why we call it an image. It's a virtual image because it appears as if light's emitting from that point. And how does this angle compare with these two? They're the same still. So we can go ahead and expand this and put in another point of reference saying that instead of having my eyes here looking at that image location, I come down here and I look further up at that image location, I can draw a line, this virtual ray through using my angles here still equal, and where they cross is where that virtual image is going to be. So we only need to do 2 of these ray analyses using these equal angles across the mirror to get the image location. However, in this lab, we're going to ask you to do 3 of them because we want to be certain that those 3 points cross at the same line. Now, this is simpler when we have a single object, but if we have an extended object, what we're going to do is throw a fit when our browser crashes. When we have an extended object like this, we're going to draw at least 2 points at the top and at least 2 points on the bottom so that we can see where the image is located. All right, obviously, it's probably because I have the recorder running at the same time. It's using up more of the computer's resources. So for an extended object, we're going to draw these lines, reflecting lines with these angles equal, extending back behind the mirror to get the location of both points on the object.
I have a question. So it doesn't matter what angle you use as long as they're both the same.
Yeah. It doesn't matter if you...
Like if 2 of the points have different angles, as long as the 2
as long as
those 2 are the same.
this angle with reference from normal is the same as this angle of the reflection, and this angle back here is the same. Now, for our activity, we're actually going to be using lines of sight to point out where the object is located and measuring these angles. So let's go ahead and do that. Let's go ahead and have everybody grab all of our groups grab a single board here. Grab, you'll need more pins as we go along, but you can just grab at least 4 pins to start with. And then grab this red see-through one. And we're going to use this as like a semi-transparent mirror. And we'll see this is more useful because we can see through it, yet it's still reflective, so we get a reflection off of it. And we're going to need at least 3 or 4 blank sheets of paper from the scratch paper area.
How many pins?
At least 3 to start with. I think for the first one, we only need 2. You have scratch paper over there. Grab a few sheets. You can grab a clear sheet, or you can grab one that has writing on the back. If you don't mind that.
No, you only get green ones.
Russell Green first. Hey, Sue, I'm Wolverine, dude. Great idea.
Okay.
Don't know if I trust you.
So we're going to start with these instructions. We're going to obtain our small mirror and our 2 pins. And we're going to place the mirror on the piece of paper and then draw a line where the mirror is located. The reason we draw this line is 1, for our measurements, but also 2, what happens if one of your lab partners is reckless and bumps your mirror? You'll know where to place the mirror back. So go ahead and grab your mirror out. And if you need to, grab one of the actual mirrors and you'll be able to see it in this plastic surface. Yeah, there's a roll of tape over there by the 3-hole punch.
Why is my lighting set?
All right, so I have my mirror set up. And again, I'm using the plastic one because I can see through it and I can see its reflection. So I'm going to put a pin out here in front and then draw, and then I'm going to look in the mirror And when you put the pin in front, can you see the reflection of the pin when you guys do it?
Oh, yeah,
You can see the reflection of the pin in back, right?
yeah.
And you could put the pin in the exact location of that reflection. Hmm.
Here.
We need.
First of all, mitochondria is fat.
All right. Did you guys all see the location there? So go ahead and look through this. Through here. Do you see the reflection of this?
Oh, you're going to do like the Twilight.
Place this pin so that this pin is exactly where that reflection is. So exactly like that. And did you already draw a line here? Yep, cool.
Like that?
Nice, yeah. So then Bree, take one of the pins and look back here. Do you see the reflection of the pin?
No, man, that's pretty off.
I see it now.
And place
I see it now.
that pin
You gotta watch that
exactly where the reflection, you see the
Yeah,
reflection.
I would impress myself with these, to be completely honest.
All right, and then we're gonna go ahead and remove this. We're gonna go ahead and remove this, and we can draw a line, right? Straight from here to here. And let's measure this distance. So this is the object, and this is the image, right? I'm gonna measure this distance. And I'm gonna get, let's see here, I got 6.8 maybe.
We got a perfect 10.
And then I'm gonna measure this other distance. Maybe I measured this first one wrong. Yeah, I got 6.8, and this one I got about 6.2. So I didn't do this 100% accurate. However, what should we have found? What do you guys think? Is the object and the image, they're going to be equal distances away?
On Earth.
How do you?
Because
I just subconsciously put it.
The old.
That's weird though, like, cause you'd think that.
because you see the reflection
Yeah, but
at that point. All right, so this is number 1 through 5. Get your answer to number 5 written down. Now I'm going to remove these pins and move on to number 6.
They should be the same. We didn't do a very good job of it.
Oh, whoops.
New piece of paper.
New piece of paper. For every one of these, you want to do a new piece of paper. So from number 6, where does it ask you to place the pin? Off to the side. So I'm going to place it over here so that I don't see it, or if I look straight at the mirror, I don't see the pin. And then I'm going to move my head over to the side. Oh, and also I ask you, as you do this, to draw it on the figures here. So you should draw it on the figure here, right? Also here, you're going to draw it on the figure here.
So you'll be able to see the reflection.
So now I'm going to move my head to the side until I do see the reflection. Okay, and then I see the reflection right there.
So now you gotta put
Can you?
You look on the object side. You're on the object side, and we want it to be, yeah, that's fine. We're supposed to be outside of the mirror.
Can't see the reflection.
Guys, it works with your laptop.
So you look into the mirror,
Just discovered that.
And when you look straight on, you can't see it. Now move your head that way so you can see the pin.
Okay.
And then put another pin.
Off to the side of the
All right, and then also
Sorta. No.
it says mark the image position, the position of your eye, and the position at the mirror that your line of sight crosses the ray image location. So that means I'm going to look in this mirror, and where my line of sight touches the mirror, I'm also going to put another pin. The reason we do that, because that's where this ray,
How did you know where to put
Oh yeah.
so go to where you can see the reflection still.
Oh shoot.
Where's this reflection right there?
And then put your head down, so it's going to be like right there, and where that hits the mirror. The
Oh,
Right there.
okay, now we're gonna.
Oh, that was beautiful.
Center. You see it? Okay, so like close. Like
that?
close.
Yeah, that's the one.
yeah.
Ah,
You're gonna get it right out
Yeah.
here. So not falling out,
Yeah.
so.
So then you're going to want to put it right up against after. So now that we have this, we can draw this line that goes from the object to the mirror. Object to the mirror, from the mirror to the image,
How do you find the one that's in the center? I can't see.
and then we're going to extend it past. I think it doesn't give you it on the directions, but typically this is a line that we draw a dashed line here. The virtual ray is dashed. And then this is where my eye was located.
Hey, how did you find this one? You just line it up.
Oh jeez.
Whatever you put on.
And then what are the angles that we're going to measure?
Like,
It looked like 90 degrees.
But yeah, they might be.
Pretty close.
So we're going to measure this theta incidence, theta reflection,
same thing.
and this other value theta. So which one was your object?
This, I believe this one. This was our object.
And that's your image back
I'm
there.
sorry, this was our object. This is our image.
So then lower your head until the bottom of the pin touches the bottom of the mirror. And put a pin right next to the mirror
Oh,
where that location is at the bottom of the mirror.
it's hard.
Roughly, you just want,
Give me a headache.
I guess you could choose, you could probably choose any location. Yeah, so just right up against the mirror.
I didn't even help her.
So we
So if you guys don't have your own protractors, we have them over here. Our
It doesn't seem.
photocopy.
Top one is just.
Yeah, on the image on the previous page, we just labeled it theta. So we're measuring this incidence angle, this reflected angle, and this other angle theta. Oh.
That's nice and check.
Prep some reflexes.
Physics.
We're trying to find all of those data.
All right, and then from here, I'm gonna leave it up to you guys. What we're gonna be doing is this same thing, except instead of this single line of sight, we're gonna be adding new lines of sight, right? So repeat this again, adding additional lines of sight here by moving your head around and putting your eyes in different locations. So you're going to end up, just like we had on this page, you're going to have 3 lines of sight for that one pin on the next part. And then after that, you're going to do it one more time and do it with an extended object. And then the rest of this is practice.